Where should I put it? Look. Look.
Yep.
It doesn't look like kinetics.
Beer's law is used in kinetics. Mass spec is not at all part of kinetics.
Okay.
Jose sideways, awesome. Jose lives in, oh God, what was that movie? Inception. Like all sorts of sideways and stuff. All right, so let's get started. All right, so before we start, let's talk real quick about yesterday's question of the day, even though I think most of you guys got it right. But just real quick, we'll recap it. I'll post the key as well afterwards. But just to make sure, if anybody that's here has any questions on it, let me just go over all of your answers. So the first part, what happens to the rate as temperature is increased? So no matter what happens, temperature always increases the rate of a reaction. Always, always, always. It doesn't matter if the reaction is endothermic or exothermic, all right? The temperature will always increase the rate of the reaction. So don't let the fact that for this problem, delta H was negative, it means it's an exothermic reaction. That doesn't mean anything with respect to rate. All right, so again, temperature always increases the rate of reaction regardless of the type of reaction. Okay, all right. Part two, it is found that the concentration of H2 affects the rate of the reaction with a ratio of 1:1, while the concentration of I2 has no effect on the rate of the reaction. What is the rate law? So if we know it's a 1:1 ratio, then we know the H2 is first order, and then the I2 has no effect, so it's zero order. So the rate would be rate equals K times H2. All right. And then for the last question, if that's the non-catalyzed reaction that's provided for us, right, then the catalyzed reaction should start at the same spot, it should end at the same spot, but the activation energy hill or hump should be smaller than the one provided for you. Okay? It does not change the overall delta H of the reaction, so that's why the starting point, end point are still the same. It doesn't make it, if it's exothermic, doesn't make it endothermic or vice versa. That all stays the same. All it does is lowers the activation energy and make sure the activation energy is always higher than your starting point. Otherwise, that means there is no activation energy and reactions just automatically happen without any input, and we know that's not the case of anything. Does anybody have any questions about those three problems? All right, awesome. All right, so let's do this. All right, so this is it. After Beer's law and visual spec, there is nothing new to learn.
Yay.
Yay. So pat ourselves on the back after this one. Get some ice cream or something. Okay, so Beer's law is what we're going to talk about first, and visual spectroscopy.
Ew.
Yeah, it sounds awful. So molecules in any solution absorb light. Sometimes they absorb all wavelengths of light. Sometimes you only absorb certain wavelengths of light. Right. So like, for example, let's see, Madison's shirt absorbs all colors of light because Madison's shirt is black, which means it doesn't reflect any light.
True.
Okay. And Natalie's shirt absorbs all light except for what color do you think Natalie's shirt does not absorb?
The color she's wearing.
The color she's wearing. So Natalie's shirt doesn't absorb yellow light. So whatever color the solution is, that's the one color it doesn't absorb. I don't think you have to worry about complementary colors too much. The other part is the more concentrated the solution, the darker the color appears because more light is being absorbed. And for that, think about like making iced tea or Kool-Aid. If you have a big pitcher of water and you add just a little bit of like drink mix, it barely changes color. The more and more you add, the darker and darker it gets, until it's like so dark you can tell that it's just going to be granulated sugar water and be crunchy when you drink it. It's a good teeth rotten drink. Right. This you don't have to worry about. You definitely don't need to know the wavelength or anything like that, so don't really worry about this too much. Okay. So how does a visual light spectroscopy machine work? Nobody's going to ask you to draw a diagram of a visual spectroscopy machine. Don't worry about anything like that. But basically, we take a solution, we put it in this thing off to the right that says sample solution in a cuvette. A cuvette is like a square test tube, and two sides of it are ribbed. That's where you know you put your fingers on. The other two sides are perfectly smooth. You don't touch that part. That's where the light actually travels through. And you basically place it in a machine. And then once it's in the machine, you turn on a light source. The light source goes through a prism or something to basically select what color you want to look at. And then the light travels through the solution. The more light that's absorbed, the meter will say absorptivity, and that number will go up. So the higher the absorptivity meter or reading, the more concentrated the solution. The lower the absorptivity, the less concentrated. The other way of looking about absorptivity is something called percent transmittance, or percent capital T. That's the exact opposite. That's how much light travels through the solution. So if you have a high absorptivity, you have a low transmittance. If you have a high transmittance, you have a low absorptivity. So I did skip a step. The very first step you would do is you would take a cuvette filled with distilled water, and you would run it through that, and you would set that to 0 absorptivity or 100% transmittance, and that gives the machine a baseline to run from. So that's how you do like your calibration. All right, so here's what we get, and this is why Beer's law is really good. If we plot absorbance versus concentration, you will get a linear graph. And we call this the Beer-Lambert law or Beer's law. And the equation is A equals epsilon BC. They changed it this year. It used to be A equals ABC, and they changed it to A equals epsilon BC. Capital A is absorbance. All right. Epsilon is molar absorptivity. That is a constant that's unique for every single molecule. So like each solution has its own epsilon value. B is the path length. That's the size of the cuvette. Cuvettes are standardized to 1 centimeter. So unless the problem says otherwise, you can always assume the letter B is the number 1. and C is concentration. So here's what that does for us. If we look at the equation, right, A equals epsilon BC. If B is 1, we can remove it, pretend it doesn't exist. So now we have A equals epsilon C, which is really similar to Y equals mx. So Y is absorptivity, X is concentration, and M, your slope, is the molar absorptivity. So if we look at this graph here, since we know X and Y values, we can determine the slope. And if we know the slope, we could find the absorptivity at any concentration or vice versa. So before we look at the problem, how does this apply to kinetics? Just random idea. You could add bleach to a colored solution and measure how fast the bleach removes the color, and that is a kinetics situation where you'd use Beer's law. So if you watch how fast color disappears from things, okay, then you can use Beer's law to help you determine the rate order of something.
And then you could use like the ln of A equals KT, that equation. Right?
You don't even need to, you could use that afterwards if you wanted to solve for K. And you want to find a rate from that you could definitely do that as well. But this would just be like, if you knew the order of something already, you could kind of work backwards to figure out how fast it would take for something to disappear or appear. One more thing, Beer's law only works if the solutions are colored. So you can't use the Beer's law if the solution is clear. Like you can't do this with salt water because salt water is clear. You will usually need to have a solution that has a transition metal in it because transition metals usually make colored solutions. Just as an FYI. So I don't think they would ask you this because the way the test is this year, but if they were, said, hey, would Beer's law work for, this solution that's clear? And the answer is no, because you can't measure absorbance of a clear solution. It's the same as water, so it falls apart. Let's try a problem out. So what is the concentration of a sample that has an absorbance of 0.33? Right. So we can basically first determine what if we know the X and Y values. We can do old school math and go rise over run. All right, so if we do rise over run, all right, we went from 0.2 to 0, so that's 0.2. And then we went from 0 to 2, so that's 2. So 0.2 over 2 is?
0.1.
1, right? Yeah. All right. So we want to know the concentration. So we say A, which is 0.33. Okay. We can just make the slope, which we just found as 0.1. Because it doesn't say otherwise, path length is also 1. And then we can find concentration. So it's 0.33 divided by 0.1. And that gets you 3.3. All right. And if we tried to find 0.33 over here and we drew a really straight line, which I definitely can't do normally, let alone with this horrible thing. Now this isn't even close to being linear at all. They did it this entirely, but we should get somewhere around 3.3. Yes. All right. So that's Beer's law. That's all there is to it.
Sounds good to me.
Yep, pretty easy. And then the best part is mass spec you guys did last year. You probably just don't realize you did it.
Nope, I don't.
So let's show you what that's like. Okay. Again, I don't really think you're gonna have to worry about how a mass spec machine works. All right, here's a very quick rundown. You fire atoms, basically isotopes of the same atom, through an electric field. The electric field will cause deflections, and everything that gets fired has the same kinetic energy. So if you remember the formula for kinetic energy, it's 1/2 mv squared. If they all have the same kinetic energy, the heavier the atom, the lower the velocity. So it doesn't travel as far towards the detector compared to the lighter atoms. They travel further because they have more, or they have the same kinetic energy, they have lower mass. And then a detector inside is able to determine what atoms hit where, and then I'll show you the readout it produces. And then we'll do a problem, and then you'll be like, oh, this is really easy. Okay, so here's what one would look like on the inside. All right, sample comes in, it goes through these slits, hits this electromagnetic field, and then it gets deflected up. And apparently, if you look off to the left, you have this awesome lap or desktop from like the 1980s. It looks really high tech. Yeah. And then here's the readout you get. So here is a chromium mass spec readout. So on the left side, it's signal intensity. And on the bottom, it tells you the masses, right? This is the mass to charge ratio. So 50, 52, 53, and 54. So if we wanted to find out what the average atomic mass is from this, I'll show you how we do it. Again, you guys have done it before. You probably just forgot. So here's what we would do. Find my pointer. All right. So we are going to take the mass at each percentage and multiply it by its percent. So for this first one, we have 50. And then we're going to multiply it by what do you think percentage this guy's at between 0 and 10?
5.
5, and then we have to turn it to a decimal, so 5% is really 0.05. All right, and 50 times 0.05 is 2.5. Put that below. All right, and then we repeat. So this one is going to be 52 times, and then this is at, I don't know, 85. So times 0.85. That's 44.2. Okay. Down here we have 53. And I would say this is at 10% or times 0.1. That's 5.3. And then this last guy would be 54. Now we have to just make sure our percents have to add up to what number?
100.
100. So we have 85.
They
Oh, we
already
actually have
add up to 100.
We already have to 100. So I guess we should make one of these a little less than 5. I don't know. We'll make the 50 real quick, 0.04. So that's 2. And then we'll make the 54 at 0.1 or 0.1, just so it adds up to 55 or up to 100. So that's points.
52.04. I remember doing this, man.
Right. And then at the end, we add them all together. So 2 plus 44.2 plus 5.3 plus 0.54. And then, Anthony, what did you say you got?
52.04.
There you go. And then we should make sure it makes sense. Your overall mass, this average atomic mass we found, that should correspond to basically the percentage that's the biggest. And if we look, 52 is definitively the largest percent. So our mass should be closest to it, which it is. And your mass, make sure it can't be smaller than the lowest mass, and it can't be larger than the largest mass. So it has to be, for this problem, between 50 and 54, and it most certainly is. That's mass spec. That's all there is to it. That's really
Sounds
it.
good to me.
Yeah. So I think there's like a follow-up question on the next slide. So let's just take a look at that. And then I think that's really it.
Yay.
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 All right, yeah. So based on the
Yay.
diagram, which of the isotope of chromium is most abundant? We said the 52 one. How is this justified by the weighted average atomic mass calculated in the previous prompt? The chromium 52 has the largest percentage, therefore the mass or the average atomic mass should be closest to it, and it was. And this last question, if you have 61.8 grams of elemental chromium, how many grams would be the isotope chromium 50? You would take 61.8 and you would just multiply it by the percentage from the previous graph, which we changed to 4%. So you do 61.8 times 0.04, and then that's how you would get your answer, 61.8 times 0.04.
2.472.
Thank you. So that many grams would be chromium 50. And that's it. You are officially done with material for AP Chemistry.
Let's
Red
go.
letter day. We got it
Yay.
done.
Yay.
We're the
You guys
party,
got it
a
done
virtual party.
before April.
Yay.
Cool.
That's crazy.
That is crazy.
Yay, indeed. That's awesome. I hope you guys feel accomplished, because that's pretty impressive stuff. Especially because we did it without even being in school.
Organic chem.
So, I mean,
Peace out, Ken.
yeah. All right. Does anybody have any questions about this sheet?
I don't
No,
think
sir.
Okay, so here's the deal. Tomorrow we'll do a Beer's Law question. Thursday we'll do a mass spec question. Friday I'll put together a review. Monday or Tuesday we'll do the test. And then after that we'll start reviewing. And apparently on Friday they're supposed to put out more details on the layout of the actual test for you guys. So once we find out the layout of the test, I'll start making reviews based on that layout. So if there's no multiple choice questions, which I don't think there are, I'm not gonna give you guys multiple choice questions to practice. That doesn't make any sense.
We
Yeah.
spent this whole year doing multiple choice questions.
I know.
Struggling
That's
on
like
multiple
every
choice
class,
questions.
too.
But you know what though? Those are the parts that you guys in general do, you don't do as well on. On every test you guys seem to do, you don't do as well on multiple
suck.
choice. So that's good. That means the part you guys do better with and the part that we've practiced more, you guys are gonna get to take a test on.
Yeah, we get a calculator.
Yeah.
You get a calculator,
We
like
do
all
get
that
a
good stuff.
calculator.
Yeah, then you can put all the formulas in the calculator.
Yeah, like I don't really
Yeah.
know what they're gonna do, how they're gonna like quote unquote make this test super secure. It's not really anybody's concern, but college boards, but it'll be interesting to see what they do. So, all right. Does anybody have any other questions?
Nope.
No.
All right. Well, guys, enjoy the rest of your day. Happy end of March. Congratulations again. All right. We'll celebrate when we go back to school with a big something or other. I don't know. We'll have to think of something good to do. And Jose owes us cupcakes for his birthday
Can we
from last week.
Yeah.
blow up some liquid fluorine?
Yeah, I'm
Yes.
sure I'll get some of that. Yeah, no
Yes.
problem.
Yes.
You know who probably can't beat liquid fluorine? COVID. Probably would beat the hell out of COVID, that's for sure.
Yeah, you're right.
Yes. We can cure coronavirus with liquid
Just
fluorine.
Yes,
some
and
fluorine.
the entire human race
How
at the
to
same
cure
time.
it?
It'd be perfect.
Right.
Join
it's
Or we can
fluorine.
shoot some gamma rays at it.
It'll be fine.
Oh my god.
People
All
in
right, guys,
Iran
have
are
a great
drinking
day. I'll
ethanol.
talk to you guys later.
See you.
Bye.
Bye.
Bye.